Hey, I'm a student at George Washington University, and I will talk about lossy image compression with discrete cosine transform using Matlab. Um, as you know, images are saved as pixels in memory, and pixel actually means nothing but a bunch of numbers. And as it's a grayscale image, the number is between 0 and 255. Discrete cosine transform is one of the transformations that can reveal the most important part of the input signal. In our case, the signal is pixels, input image pixels. So we'll use 4 by 4. We can actually use 8 by 8, 2 by 2, another number. And it means that if we use 4 by 4 DCT, we have to split our images to 4 by 4 blocks, and we have to multiply each one to discrete cosine transform. As you can see, when we multiply our image, pixels to the DCT 4 by 4, we get a sort of different matrix. And I actually would want to show the same thing here in Matlab, as I've used Matlab for everything. For example, as you can see, this is the original pixels of the image, and DJ, as you can see here, is transformed by a discrete cosine transform. This is our blocks. So what we'll do here actually after this, as we get this one, in our new DC transformed pixels, we will split it as DC and AC terms. DC terms are the main one single pixel of the images, and this is a very important part. So it means that we can actually show image only having the first pixel of each block. That's why we append all of these first element to the DC terms array, and for the rest of the term, it's called AC terms. This actually AC means a direct current and alternative current from physics. And here we will go, as we know, the first elements in the image, closer to DC terms, more important. That's why we will not go row by row or column by column, row by row. We will go zigzag ordering diagonally. In this case, we will start from the first one. We'll go like this, diagonally up and then down, and then up and then down, until we reach the last one. And as we go, we append each AC term through our AC terms array. And we have to do it for each block. That's why we'll go block by block and apply the same idea here. The first element will go to DC terms array, and the rest will go to the AC terms array. And at the end, we will have 1 by 4 DC terms and 4 by 4 AC terms. And that's exactly what we're going to do here. First, we'll go quantize DC, and it means that we will actually end up with DC terms. As you can see here, all the big numbers are here. Then we will do the same to the AC terms. And in AC terms, actually, that's the same loop. But here the trick is that instead of going through all n-1 elements, and just when I'm here, I'm also quantizing this one. When I'm here, quantizing this one, and it's kind of at the end, I will end up n by 2 computation. So it is like kind of a little bit speed. We earn speed. And the next thing we will quantize our DC terms slightly, but we'll quantize our AC term aggressively with uniform, semi-uniform, or max-load quantizers. It's up to us. And at the end, we will save image in terms of DC and AC terms, and we can achieve compression ratio between 10 and 27. This is a huge compression ratio. It means that if you have 1 megabyte of, you have image of 1 megabyte, you can end up 100 kilobytes. So this is a huge compression here. And for example, as one of the approximation, this is the original image, and we can end up this kind of recovered image. And this is actually a very aggressive compression. And for example, I will show here, this is like end image. So this is about 15 compression ratio. This is huge. That's how we can use Matlab for loss image compression, actually. Thank you.